I think it's recording. Okay, it's recording now. Sorry, guys, I missed the first little bit of recording. Remind me if I forget to record in future, okay? Because otherwise you guys won't get to double check this class again. All right, so again, we went through naming alkanes, alkenes, alkynes, brief mention about cyclic hydrocarbons. Cyclic hydrocarbons have a closed main chain. That is a difference, right? If you're playing the game of snakes and ladders, this time you can keep looping around and around and around the main chain. It's closed versus a linear, disjuncted or non-closed main chain that has a clear start point and a clear finish point. Okay? I want you to have a look at this and tell me, what would you call this compound? What's the longest main chain we see? 1, 2, 3, 4, 5, 6, right? So if it was a linear hydrocarbon, you'd call it hexane. Since it is a cyclic hydrocarbon, you'll simply add cyclohexane. Now, I'm going to give you guys a couple seconds to think about this. What is the general chemical formula of a cycloalkane? Use cyclohexane as your example. What I'm asking you is when C is equal to N, what will H be equal to with a cycloalkane? Hit the raise hand icon once you've got an answer. Very good. Very quick. Let's go to Akshita.
When C equals to N, H is equal to 2N.
Good. So what you realize is your cycloalkanes have the same chemical formula as alkenes. The cycloalkenes will have the same chemical formula as alkynes. And the cycloalkynes will be CnH2n minus 4. I've never ever done a question with a cycloalkyne, so I wouldn't even worry if I was you. Okay, as long as you remember that little pattern. The next thing is to do with numbers, right? What I mean by that is, what if I just did this? What would you name this compound now? Hit the raise hand icon once you've got an answer. Ruthania, what's your answer?
Would it be 3-methyl cyclohexane?
Okay, let me ask you, why did you give it the 3 position?
And it just counted clockwise.
Okay, who was carbon number 1?
The top one.
Okay, but this is where you have to think spatially, right? What if, like a wheel, you turned it 90 degrees? Who's your carbon number 1 then? So what I'm asking you is, your top, or your 12 o'clock position, really depends on which angle you're looking at this molecule from, right? If you rotate the molecule 180, then the 6 o'clock position becomes a 12 o'clock position. And so that's now carbon number 1 according to you. So do you agree that your definition of carbon number 1 is a bit redundant, because it really varies at which angle you're looking at this cyclic hydrocarbon? So Ethan, what do you think? What would you call this compound?
I was just wondering, would it change to like a heptane? Because the longest change becomes 7.
Does it become 7? Because think about it. Let's say I know, I'm just going to start with it. Tanya said you go up there, you come back here.
If we start with the CH3 and then go clockwise, it can become 7, right?
You're right, partially, but that's not how we would count because it's a closed loop. It doesn't make sense to count. It would make sense to count like that if this carbon wasn't connected, right? So you're saying we should count like this all the way to there. It just doesn't make sense. Because if we come back to this, we've counted this carbon twice. Do you agree? And if we don't count that, then we haven't accounted for this bond here. So what I mean to say is that the ring is always going to be, this is always going to be your main chain. Yes? This is never going to be part of your main chain. Okay? But my question is, what are you calling this compound? We haven't got it yet. Let's go to Ethan. Ethan, back to you because you didn't answer my question. What would you call this? You said heptane. Is that your answer? If so, it's a very good thought.
Yeah, I was
Sid?
just guessing.
Yeah, that's fine. I want you guys to guess. What I'm trying to get you guys to do is learn how to think in terms of IUPAC. Because once you understand what IUPAC prioritizes in terms of naming, you will know how to apply it on the spot to new questions. Sid, what would you call this compound?
1-methyl cyclohexane.
Yeah, I would agree with you. And the reason is carbon number 1 is arbitrary. Remember, we're trying to give the alkyl groups the lowest number here because there's no double bond, there's no triple bond. So why would we make this carbon number 1? Why would we make this carbon number 1 when we can simplify things and make this carbon number 1? And remember, we should always state the alkyl group positions. Always state the alkyl group positions. So I'd agree. This is 1-methyl cyclohexane. So what I do again is I apply the longest main chain, which is just this. And I go, well, do I go left, right, or right to left? Well, there's no left to right, right to left anymore. It's a cycle, right? There's no start or finish point. What we can do instead is make this our start point solely to give this methyl group the lowest number. Similarly, what would you call this? Okay. When you guys have got an answer, hit the raise hand icon. Very quick. Good. Mohammed, this one's your turn. Whenever you're ready. What are the steps in naming a hydrocarbon?
Can you hear me? One in the long chain and then numbering it. But since it's a circle, a closed main chain, my train of thought is, what if they all became one and you just continue counting upwards if they have more? Does that make sense?
So what would your name be for this compound?
So it would be 1, 2 bromo, and then 1 chloro, 1 fluoro, and then cyclohexane.
Okay, good thought. I like how you're trying to give everything the lowest number. But in this case, you have to think about reverse engineering it, right? When you say a name to me, I should be able to close my eyes and never look at this image in my life. I should be able to draw it from scratch. So what you've said is 1, 2. Could you repeat? I'm just going to act like I've never seen this compound before. This is a really good test if you're really unsure. So could you repeat what you said to me?
1, 2 bromo.
Okay. Yep, keep going.
Was it 1 chloro?
Yes. That's what you said.
And 1 fluoro.
Yeah.
And then it was cyclohexane.
Okay, so I go, all right. So he's told me I've got a cyclohexane main chain, so I'm going to draw that first. And then in the first position, I've just made this arbitrarily my 1. I could have made any of these carbons my 1 position. He said there's a fluoro, there's a bromo, there's a chloro, and he said at the 2 position there's a bromo. Does this look, Mohammed, like your image up here? Not. No, it doesn't. Good, good. So now you start to understand, I need to state their relative positions. Agree? What was not exactly right in our earlier example was we did not account for the relative positions of these different halogen groups. Ethan, your turn.
I started with the chloro, so I wrote 1 chloro, 3
Why did you start
dibro.
with 1 chloro?
Because like at like the 3rd carbon is dibromo, so like C comes before D, so I start like that.
Do you prioritize alphabetical order first, or do you try giving the entire chain the lowest sum number first?
Oh yeah.
Good. So revise your answer. Who's carbon number 1?
1 dibromo.
Good. So I would make this my carbon number 1 most logically, because it's got 2 alkyl groups on it, or 2 halogen groups, and I want to give both those the lowest number, because if I pick any other carbon as 1, those 2 bromine groups are going to get a number greater than 1, and the total sum will be much more. If I made this carbon number 1, then those bromines will get at least a 3 and a 3, which will give me a sum of at least 6, which is a huge number, right? So I can go, all right, this is 1. I can go make it 1, 2, 3, 4, 5, 6. And I can also choose to count outside and go 1, go the other way, 2, 3, 4, 5, 6. Which way am I going to go? So let's go now to Akshita. Akshita, I want to go left to right. What's my chain sum? Or clockwise, what's my sum? Quickly. What's the sum, Akshita?
10, was it?
Just go one by one. So it's 1 plus 1
1
plus
plus-
what?
Okay, 1 plus 1 plus 6 plus.
Is it 6? Look, we're counting in blue, right? Because we're going clockwise.
Oh, okay, sorry. Plus 3 plus 6.
Good, right? Which gives us a
That's
total
11.
sum of 11. Agree?
Yeah.
Good. That's why it's always important to break it down instead of getting a final answer. So if I go right to left, which is in red, Sid, what do I get?
You get 1 plus 1 plus 3 plus 6.
So Sid, now the question is, which way do I go? Equal
Wait,
sums.
I just have a question.
Yeah.
I think the 5 is placed wrong.
Oh, yes, it is. 1, 2, 3, 4. Yes, it is. Good pickup. Very good pickup. Good job. This is 4. This is 5. This is 6. Good job. And I'll just make sure I've done it right on the other one. Good. I think the sum wouldn't be the same now. So it will be 1 plus 1 plus 3 plus 5. I almost accidentally duped you guys. Good. That'll be 10. All right. So now we have a clear direction we're going to go. But I just wanted to say, if it was equal numbers both ways, you would have gone the direction that gave the chlorine the lowest number alphabetically, right? Because a bromine, which is the first letter, is getting a 1 regardless. You go the direction that gives chlorine the lowest number. Question set?
It is the same sum.
Is it? What?
You wrote 6 twice.
Oh my God, my counting is ridiculous. All right. Good. Good pickup again. All right, let me go back here. I don't know what's going on. Maybe my brain is fried. All right. So it should be, let me do it again from left to right myself so everyone is on the same page. Okay? All right. So this is 1 plus 1. This is going clockwise. It'll be 1 plus 1 plus 3 plus 5 equals to 10. And then right to left, it'll be 1 plus 1 plus 3 plus 5, which is also equal to 10. Good. All right. So we are facing the predicament I mentioned. So I think I've answered it. Mohammed, which way are you going now? Are you going to follow the blue or the red? Sorry, I can't hear you.
See the blue.
Good, because it gives a chlorine a lower number compared to if you went through the red direction. Okay, so now what we can do is rub out the red numbers and we can start naming this compound. So let's get Ethan. Can you name this for us?
So it's 1 dibromo.
Is it 1 dibromo? You need to state all the positions, so all the locations, and then you can tell me the number. So location and number. So where are the 2 bromines?
With carbon number 1.
Good.
Oh.
So it's 1, 1. Does that make sense?
Yeah.
If you say 1 dibromo, I'm thinking he's told me there's only 1 bromine, but he said there's 2 in the next part of the word, right?
Yeah.
So 1, 1 dash dibromo. Keep going.
3 chloro.
Dash 3 chloro.
Yeah. 5
Keep
dash
going.
fluoro.
Dash 5 dash
chlorhexane.
fluoro. Cyclohexane. All 1. I'm just going to the next line because I can't fit it all. Cyclohexane. Good. See, you guys are answering these really hard naming ones that are very long. Maybe I can just put it in one. Just take this all off. Cyclohexane. Good. And if you're still confused as to whether you're at the right word, you can double, triple check. And you can always try drawing it without looking and seeing whether you drew the exact same compound. And if you did, then you've named it correctly. Okay, good. Now, I just want to preface, even though we spent quite a bit of time on cyclic hydrocarbons, they are low yield. They'll only come up most likely in your trials, and they will not be as hard as this example that we did. I just wanted to give you some more challenging ones. So if you do get a hard naming question, it's still quite comfortable and within your scope versus a student that's never seen this, for example, would probably make a ton of mistakes. Okay, very good. Good. Let's move on from alkenes. Let's go to very brief mention with alkynes. It's the exact same as alkenes. You will literally just change the suffix to alkyne. So I want you guys to just eyeball this. Let's go to Akshita. Eyeballing this, what would you call this compound?
Butane.
Very good. Oh, ask yourself, do I need to state the triple bond position? And that's a final question. And to answer that question, what do we do, Akshita?
Flip it.
You don't even have to flip it. You can literally move, just move it one position and see, does it change the name?
Yes.
Good. So can you revise your naming? What do you call this?
But 1 I.
Good. Right. What about this one? What would you call this one here and this one here? And not Akshita. Let's get Ruthania. I want you to name 2. And Ethan, I want you to name number 1. We'll start with Akshit. We'll start with Ethan. Can you name number 1 for us?
Sorry. It's wait. It's ethene. Yeah.
Ethene?
Oh, no, wait.
Remember, it's an alkyne, right? Because it's got 3 bonds. So it's just ethyne.
Ethine.
That's it. That's it. Okay. Good. Ruthania, on to you.
Propine.
Very good. Why did you not say prop 19?
Because if you move the bond, it doesn't really change.
Good, right? So now you're starting to all get the little nuances with naming. Very good. That's literally it. We're done with alkynes. I don't think in the last 7 years I've ever done an alkyne or seen an alkyne naming question. Because I know if you can name an alkene, you can name an alkyne. It's very simple, right? Now, this point here, geometric shapes around carbon, you would be surprised how high yield it is, especially for trials. They love asking you what the bond angle is depending on the number of bonds carbon has. So I need you guys to double pay attention to this part. You will either get it as a MCQ question in your trials, or you might get it in your HSC. They love asking this in an exam point of view, even though I don't think it's as important in the topic of organic chemistry. Okay? The first point is if a carbon molecule has 4 surrounding bonds. Remember, it always has 4 surrounding bonds. But what I mean is 4 single bonds around it, it'll form a tetrahedral arrangement. And remember, each line represents an electron pair. And what every electron pair is trying to do, since they're all negatively charged, is get as far away from each other in the axis of space-time. Right? So in space, they're trying to move far away from one another. Now, if you have 2 hands, you can imagine each hand is an electron pair. If you wanted these hands to be as far apart from one another, you just put them like this, like a 180-degree angle like this, right? But if you have 4 bonds, you can see some of the bonds will come out of the page to try hit your face. So this bond here will be coming out of the page towards you. These 2 bonds will be moving more backwards, right? Kind of like a tripod. And this bond here will be shooting up to the sky. And if you measure the bond angle there, you need to memorize this. The bond angle will be 109.5 degrees. Okay, this is one of the few times in organic chem, especially for your trials, especially if you go to a selective school, you should memorize this. Good. My next point is when you have 4 bonds, but they're arranged as a double bond. See, unlike the bond above, which is 4 single bonds, you now have 1 double bond and 2 single bonds, right? You will obtain this planar arrangement shape. The way I remember this is it's kind of like a pie. Can you all see that? Like a pie. And if you chop a pie into thirds, the angle between is 120 degrees. That is a bond angle, and it's called a planar arrangement, according to Vesiper theory. So remember, the bond angle is 120 degrees. This is probably the most high-yield bond angle. Can someone give me an example of a molecule, a hydrocarbon molecule, that would have a tetrahedral arrangement? Let's go to Sid. Give me an example of an alkane, Sid, that would have a tetrahedral arrangement around its carbon.
Methane.
Yeah, good. The question I asked sounded really fancy, but it's very simple. So technically, when we're drawing it like this, everyone, it's not right. That's not actually how the molecule is in space. And that's why there's ball and stick models. If anyone's played, can you hit the race icon if you've connected the ball and stick model molecules together? Yeah, right. When you do it, do you realize that the bonds are going in different angles? Like then you never get a ball and stick that looks like this. If you were to do a ball and stick with a carbon and 4 other atoms, it would end up looking like this, a tripod with a roof, not a roof, an arm projecting up into the sky. I could try physically showing you, but I'd look a little too awkward. All right, good. So now this is a high-yield part. With a planar arrangement, actually, can you give me an example of a hydrocarbon that would have a planar arrangement? Oh, damn, the examples are there, but hopefully you didn't read that.
Propene.
Let's see. We draw it out. Propene looks like this. And the way they'll ask you in an exam, is they'll say this is carbon number A, this is carbon number B, this is carbon number C. An MCQ question will be, which of the following carbons has a trigonal planar arrangement? And actually, what would you say? Is it carbon number A, B, or C that has a trigonal planar arrangement?
Carbon number 3.
There's letters A, B, or C. Which one are you picking?
Okay, A.
Good. I agree with you. Do you see A is the one carbon that has a double bond and 2 single bonds? And I've drawn it like this to confuse you because the expanded structural formula does not account for bond angles. So whatever we're drawing here is not right. This is just for simplicity's purpose. In reality, it should be drawn kind of like this. Something like that. Okay, and this carbon will have a tetrahedral arrangement of all of its atoms. They should be 109 degrees apart, 0.5 degrees. And this carbon will have all of its bonds that are 120 degrees apart. So the answer was carbon A. The simplest example of this with a 120-degree bond angle is ethene. Ethene looks like this. So I want you all to remember, ethene is probably one of the most important molecules in all of organic chemistry, and it has a trigonal planar arrangement of all of its carbons, carbon number 1 and carbon number 2. Okay, good. The rest are very intuitive. You can kind of remember every other bond angle is going to give you a linear arrangement. Linear, 180 degrees, low yield. So I'd say arguably, these are the two important bond angles and names you need to know. Everything else is going to be linear. Any questions, everyone? Good. Good job. Already spoken about cyclic hydrocarbons. The only other thing to mention, what do we call this, the name when we draw it in this specific arrangement or symbolization? So this is expanded structural formula. What is this called? This is called skeletal formula. Okay, expanded structural, skeletal. You guys are never to draw a hydrocarbon like this. You'll get it wrong if you do so. Always draw it in expanded structural. The other thing you will see is they might draw it in, so what is this? This is 1, 2, 3, 4, 5. This is cyclopentane, pentane. So you may see it drawn like this. Does anyone know what we call this type of drawing? Actually, though, you've done organic chemistry, right? What would you call this?
Structural, was it?
So this is expanded structural. This is skeletal. What is this called? It is structural, but there's a name in front of it.
Simplified.
It's condensed structural. The reason is they'll just ask you to draw it in a specific way. If you don't know what that means, you won't be able to draw it. Okay? Expanded structural, skeletal, and condensed structural. Very good. Yeah, they end up looking like UCAT images for your is it the mathematical section? I forgot the names. It's been 7 years. All right. But back in my day, we did the UMAT, which was 3 hours, and I remember just getting so mentally exhausted towards the end of the exam. I just guessed the last 10 questions and just chilled because I needed a break. But that exam is a whole other situation. The good thing, guys, about your HSC is all of you, as long as you put the work in an actual exam, you'll finish early. You'll finish with like at least 20 minutes. Sometimes with my chem exam, I finished with like 45 minutes left. And so the rest of the exam, I was just I was double checking. I never relaxed because you should never just chill and close a book unless you are sure you got 100, which is virtually impossible. Only like 2 or 1 or no people will get that mark. But at least you can just take a bit of a breather that you know you've finished. Whereas in the UCAT, especially the UMAT exam, it's 100% brain power. All right, one thing to mention here. Everything I've taught you till date, and everything I will teach you after this, will be about hydrocarbons that do not contain this molecule called benzene. So when we say the word hydrocarbon, we're talking about any compound that contains a H and a C. Now, under this huge kingdom of hydrocarbons, we can have what's called aromatic hydrocarbons, or we can have what's called aliphatic hydrocarbons. They're aliphatic when there is no benzene. Benzenes are not allowed in this club. And in aromatic hydrocarbons, they do contain benzene. And the reason it's called aromatic is because the addition of this benzene molecule usually adds a unique aroma or smell to the hydrocarbon. Okay, interestingly, benzene is also carcinogenic, and I'm pretty sure it's in cigarette smoke. So if you really want to get into organic chemistry, don't ever smoke. I'm not advocating smoking, but benzene is one of the most carcinogenic compounds in cigarette smoke that people inhale. So, a bit about benzene. Benzene is not like your typical hydrocarbon. What I mean by that is, at superficial glance, you might go, oh, this is just a cyclic hydrocarbon. What makes it so special that it gets its own unique name? Now, with benzene, what's interesting is, well, this is technically the structure of benzene, right? What I'm drawing in front of you here. 1, 2, 3, 4, H, 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 right? So you could probably argue, wait, isn't this just, I don't know, what would you call this? 1, 2, 3, 4, 5, 6. Isn't just 1, 2, 3, 4, 5, 6 hex 1, 3, 5 triene? Can't we just call it this compound? The answer is no, not at all. That's a completely different compound. The reason is the inner bonds, these electrons here, this electron pair here, this electron pair here, this electron pair here, are not fixed. What they actually do is they end up forming a little sea of delocalized electrons, this little sea of 6 delocalized electrons that spins around the inside of the cyclic hydrocarbon like a F1 race course, right? So it's not your typical hydrocarbon because of the sea of delocalized electrons, and because of that, benzene engages in very unique reactions that make it completely different to the rest of organic chemistry. Hence, why we need a whole system of separation when a compound contains benzene versus when it doesn't contain benzene. A simplified image of benzene you will see is this hexagon with a circle inside, and the circle represents the sea of delocalized inner electrons. Okay? Benzene is probably the most important functional group ever, or one of the most important functional groups in hydrocarbons, such that it's more important than a double bond, more important than a triple bond, more important than virtually every other functional group you're going to learn after this point. Good news is, for HSC, they pretty much just do this, meaning you will not look at any naming of compounds that contain benzene. All your naming will be about aliphatic hydrocarbons. As long as you can appreciate Mod 7 is all about aliphatic organic chemistry, not aromatic organic chemistry. Good. I'll give you a break now. You can have a 5-minute break and then we'll recap at about 6:11, 6:12. Any questions before we take a little break? Good. Good job. All right. Mohammed, question before the break?
I didn't get that part, you know, when naming alkanes, alkenes, and alkynes. What was that equation you gave for all of them? I didn't get that part.
Okay.
SCH.
The CNH
Yeah, that.
endpoint. Yeah, so Mohammed, the general rule for naming an alkane is CnH2n plus 2. What this means is when the number of carbons is equal to n, the number of hydrogens will always be 2n plus 2. Let me give you an example. If I have methane, right, Mohammed? What is n equal to? N is equal to 1. There's only one carbon. You agree? The number of hydrogens will be equal to 2n plus 2. So it'll be equal to 2. So the number of hydrogens will be equal to 2n plus 2, which is 2 times 1 plus 2, which is equal to 4. Can you see how there's 4 hydrogens? It's kind of a shortcut. So, Mohammed, if I say, can you name the chemical formula of decane, you might, if you don't know this formula, you'll have to draw decane and then count the carbons, count the hydrogens. But someone who remembers this formula will go, well, in decane, n is equal to 10, so H is equal to 2n plus 2, or 22. Does that make sense?
I understand. The
Good.
quicker way of counting the carbons and hydrogens.
Yes, that's it. Just a quick way of counting the number of hydrogens when you know the number of carbons with alkanes, alkenes, and alkynes. Alkenes is CnH2n, alkynes is CnH2n minus 2. Good. All right, take your break. We'll recap at about 6:14, 6:13. All right? See you guys in a bit. Okay, can you guys hit the raise hand icon? And we'll jump to the rest of naming. Cool. I know, Sid, you play cricket. Does anyone else play any sport here? Or I don't know if you guys gym or exercise or run or cycle. Very good, good. You know, exercise is one of the few things that is scientifically proven to chemically change your brain and make you smarter and also happier. There was a huge study done and they found that it increases the amount of dopamine in your prefrontal cortex, which is right in the center of the brain. You might notice after you do exercise or play sport, you feel pretty good. And that's literally due to the dopamine release. So I would say for your mental health this year, and if you want to be smarter, do something for your physical health as well. And it'll help your mental health. It's all like an interrelated web. Good. All right, let's go to isomers. Isomers are an amazing test of your spatial understanding. Okay, we'll first talk about what the word isomer means. Does anyone know what this word means? Akshita, can you explain to the class, what does isomer mean?
So an isomer is basically when two compounds, they might have the same chemical formula, but they're like structured differently, or yeah.
Yeah, so quite literally, same chemical formula, different structural formula. That's it, right? So the exact same chemical number of carbons and hydrogens, but drawn out, they're a different compound. Let's go through a very simple example of this, right? If I was to show you, let's say, C3 to C4H9, right? This is a chemical formula. And from this chemical formula, I can either have this compound being, sorry, not C4H9, C4H10. I can either have this compound being butane, or I can have this compound also looking like this. Right? You can clearly see the structural formula looks different. Don't worry about their names for now, but they have the exact same chemical formula. So we'd call these two compounds isomers. Okay. Now, under the category of isomers is different kinds of isomers. And the syllabus doesn't really clarify how they're all related, but I'm going to make it very clear for us. When we have isomers, the first type of isomer you have is called a chain isomer. Okay, and that is when you have different main chain configurations. Example of this is looking here. This is pretty much what I just drew. When you have the chemical formula of C4H10, there are two different chain isomers you can have. You can have a main chain that's made out of 4 carbons, or you can have a main chain that is made out of 3 carbons with an alkyl group in the middle. Don't worry about the alkyl group in the middle. The fact that option A and B have different main chains makes them a chain isomer. Okay. Now within a chain isomer, so then zooming now into a chain isomer, you can have the different position of alkyl groups. So you can see here, there's no alkyl group around this 4-carbon main chain. So it doesn't apply. There are no positional isomers here. But let's say that there was a chlorine in this compound, right? We can see that the chlorine in this main chain can occupy the first position where it's bonding to carbon number 1, or it can be bonded in the second position where it's bonded to carbon number 2. And now we have two different positional isomers within this chain isomer. And so again, what I'm trying to show you is you can have chain isomers where the main chain is different, and within a chain isomer, you can have positional isomers. And positional isomers are when the position of the alkyl group or the halogen group within that fixed main chain is moved to another position. I remember in my year 12 school exams, on one of my chem exams, I only lost 1 mark. I think it was my trials. And the 1 mark I lost was an isomer question because I made a silly mistake. So just to show you, you have to be very careful when you are finding the number of isomers in a compound. Okay, I will give you an example question to do. Identify the number of isomers this compound can have. So start by playing around with it. I'm going to give you about a minute to play around with it because you need to start problem solving yourself. And then I'll show you how I'll break it down to make sure you exhaustively get all the different isomers without missing any. Okay, there's about 40 more seconds. Hit the raise hand icon if you think you've got all the isomers.
Is it C4H9?
Sorry, it should be C4H9Br. Sorry, good pickup, Akshita. The reason I keep putting 9 was I still remember to this day in my year 12 exam, this was the isomer I got. And if I'd known, or if I had a systematic way of getting all the isomers, I wouldn't have missed a silly one. Yeah. Yeah, C4H9Br. All right, Akshita, how many isomers did you get?
I got 4.
Let's see. So this is how I break down isomers when I do these questions now, okay? I start by finding all the different main chains I can have. So the 4-carbon molecule, Sid, what are the different main chains I can have?
So you can have 4 straight.
Yeah, what else can you have?
Then you can have 3 and then 1 methyl group.
Good. So there are 2 chain isomers, as we can all appreciate. Be careful what the question asks you. If they ask you for chain isomers, this is the answer. There's 2 chain isomers. Now, going to the first one, Ruthania, how many positional isomers can we have? Now, when it comes to positional isomers, Ruthania, this is where we have to start thinking with that fixed main chain, what alkyl or substituent groups can move around it? So what's a substituent we have in this compound? Ruthania?
Bromo.
Good. So we can put it in the first position. What would it be called?
1-bromo.
Yeah, so this is a butane main chain. So now it would be called 1-bromo butane. I'm just going to put 1-bromo B. What if I moved it? I just be exhaustive. I move it in every position possible. At your stage now, you should be moving the alkyl groups everywhere you can. What if I move it here? What would it be called?
2-bromo.
Good. So now we have a 2-bromobutane. What if I move it here? Actually, I thought what would it be called then?
2 as well.
Good. Sorry, I did 1 and 2. Good. So that doesn't count. What if I move it here?
One as well, like
Good.
just one.
Good. So that doesn't count as well. So there are 2 positional isomers under the chain isomer of butane. Sid, onto you with number 2. What are the different positions that we can have for our butane?
So you can have it in the first,
You-
on the methyl group as well.
Good. Good. You can have it in the methyl group. What would it be called then if it was here?
Then it would be called 1-bromo 2 methyl propane.
Yeah, good. So it'd be called 1-bromo 2-methylpropane, but so this is your 2-methylpropane, right? 2-methylpropane.
It would be
So,
the same.
yeah, so that way it doesn't matter if it can't move there. What if it moves here? What would it be called then?
It'd be 2-bromo 2-methyl.
Good. Yeah, it'd be 2-bromo 2-methylpropane, right? What if it was moved there? What would it be called?
It'd be the same as the first. So
Good.
1.
Good. And we move it there, we're back to square one. So in total, how many isomers do we have?
2.
Good.
Oh,
And overall, yeah, so we have 2 there, I get what you were saying, and then 2 here. So in total, we have 4 isomers. So whenever a question just asks you for number of isomers, what they're actually asking is a number of positional isomers combined for all the different chain isomers. That's what number of isomers means. If they're asking for chain isomers specifically or positional isomers specifically, they will mention it. Okay? Very good. Actually, is this what you got?
Yeah, I got that, and I have a question. You know, when you did the CC and like you put the second variant, like how you put the methyl propane, right? Can we bring the C to make it an ethyl as well?
How so? As in, like, put it at the end like this?
No, like as in put both the C's on the second carbon.
Okay, so you mean like this, is that right?
Yeah, or
Okay,
like
but
under each other.
yeah, so if you get this compound and then you rotate this end, you rotate it up here, and you rotate this end, you bring it down here, you get this compound. You
What if we
can't,
put it like under each other? Like the
okay,
C, like
okay, let's do that, right? So you get the 2 carbons and you put under each other like this.
yeah.
Then the longest main chain is butane now. It's just a butane at right angles.
Okay.
Yeah. Good thought. Good thought. But I really like that you thought about it like that. The only reason I didn't do that is I've seen this compound a lot, and so I knew that would just make butane again. But I think everyone should try making more main chains. But yeah, you're right. If you do that, always ask yourself, well, what is the longest main chain now? Now it's still 4. So you're back to butane. So these are the only isomers you can have. Okay, good. Any questions? Good. When I was in Year 12, I didn't have a system of doing this, and hence why I think I missed one by silly mistake. So always remember, start with chain isomers, find all the possible different main chains you can have, and then within each main chain, you will then need to move the positions around. Now, another tip, let's go through one more compound just to make it a little bit more challenging for you. What if you have something like C? I don't want to make it too hard, because the second you increase the number of carbons, it gets much harder. So the C5H10BrCl. This is going to be a hard one. Hard one in the sense that it will take more time. So I'll give you guys about 2 minutes for this. Okay, hit the raise hand icon once you've got an answer. Good. Get some water. Okay, how do we go? Let's start with Ethan. What's the first step?
Draw the main chains.
Okay, so what are the different main chains you can have?
I did one with like a straight line first.
Okay, what else can we have?
Not quite sure. Got a bit stuck as well.
So you're telling me there's no other main chain you can think of apart from 5 consecutive carbons?
So you can have like 4 carbons and oh no wait, yeah, that's the same.
No, you're right. You can have 4 carbons and one like this.
Yeah, 4 carbons and
Good. Yeah, be
Yeah.
confident in yourself. Yeah, you can have 4 carbons and one like this, right? What else can you have? Can you have 3 carbons?
3 carbons and 2 going up or down.
Yeah, you can have 3 carbons, and can you have this and this?
Yeah.
Yeah, I think so. Can you have 4 carbons and this carbon being here? Well, technically, this is another positional isomer. The main chain is still 4, but does everyone appreciate this is identical to this? So it doesn't matter either way. Yeah? Good, because this is carbon number 1, this would be carbon number 1 now, so same thing. Can you have less than 3 carbons? Probably not, because you couldn't have less than 3 carbons with a butane, so that should teach you probably can't have less than 3 carbons with a pentane. You can try putting it there. You can try making 2 carbons and 1 there and 1 there and 1 there, 1, 2, 3, 4, 5. But then that's just this, right? So what you should all be trying to do is play around and get as many different main chains as you can. Can anyone think of any other main chains in this? I think this is all the main chains you can have. Yep, you shouldn't have any other main chains. Good. So now what do you do? Within a main chain, we'll start with the easiest one. This main chain here, what are the different positional isomers we can have? So underneath that, we can go 1, 2, 3, 4, 5. We've got a Br and a Cl. So how are we going to play this game and get all the different positional isomers? Everyone? So here's my tip. You lock one of the substituents and you move the other one around everywhere. And then you move the substituent one position and you repeat. So what I mean by that is we can fix, well, let's just pick randomly. Let's just pick the bromine. We're going to fix that. So when the bromine is in the 1 position, we can have the chlorine in the 1 position, right? So this is going to be 1 bromo, 1 chloro. Everyone with me? If I move it here, Ruthania, what would you call it? So here, 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 and here. So very quickly tell me which ones will give me new names.
Moving it to the right once and then again would give you different names.
Good. I need the names, so quickly tell me.
Okay. 1 bromo, 2 chloro.
Good.
And then will be 1 bromo, 3 chloro.
Good. What if you move it to the very end?
It will be 1 bromo, 1. Oh wait. Is the bromo still staying in the same spot?
Yeah, it's not moving. Remember, what do we say? We are locking one of the substituents. We're not moving it. One variable at a time. So when you move that to the very end, what would it be called?
1 bromo.
4 chloro. Remember, alphabetical order. If they're both at the opposite ends, you want to give the bromo the smaller number. Very good. So we've got 4 isomers just in that. What if we now move the... So again, draw it again. 2, 3, 4, 5, but lock the bromine in the 2nd position. What can we have? So if the chlorine is here, what would we call this? Someone quickly tell me. Let's go to Sid. Finish it off for me. Here, 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 here. What would you call it?
2 bromo, 1 chloro, and
Yeah,
then it
good.
2
Sorry,
bro
I put it in the wrong order. So it'd be 2 bromo, 1 chloro. Good. Keep going.
2 bromo, 2 chloro,
Yeah,
2 bromo, 3 chloro, 2
good.
bromo, 4 chloro, and 2 bromo, 5 chloro.
Yeah, think about whether it be 2 bromo 5 chloro if it was here. Just be cautious with the naming, right? So if the chlorine was here, could it be 1, 2, 3, 4? Could it be 1 and 4 rather than 2 bromo 5 chloro?
Yeah, okay, yeah.
Good. So again, repeat it for me. What would it be if it was so we've done this, we've done 2 bromo 3 chloro. What if it was here? What would you call it then?
If it was there, then yeah, it'd still be 2 bromo, 4 chloro, because the
Yep.
bromo, yeah.
Good. 2 bromo 4 chloro. Good. And if it was at the very end?
4 bromo, 1 chloro.
Yeah, because this would be carbon number 1. Very good. 4 bromo 1 chloro. Very good. And again, you have to then move it to 3rd position. We're not going to go through all the other options, but can you all see the second you add 2 substituents, how many more different isomers you get? So you won't get an option this hard in your exams or this long and tedious. This is just to show you how to approach a question like this. So now you'd have to lock the bromine in the 3rd position and start again. So when it's here, what would you call this? Let's go now to Mohammed.
Bromo, 1,
Louder, Mohammed, I can't hear you.
3 bromo, 1 chloro.
Good. 3 bromo, 1 chloro. Good.
Just one
What?
question.
Yep.
How would you know the ones that you can't like reuse? Do you understand what I mean? Like some of them You can't use like example the 5 bromo, the 5 chloro. Sorry.
What do you mean? We'll get to it and then we'll go through it. So it's 3 bromo, 1 chloro. If we move it to this position, what would it be called?
3 bromo, 2 chloro.
Yeah. Yeah. Good. So this would be 3 bromo, 2 chloro. I'm just thinking, can we name it shorter? No, we can't. What if it moves to this position?
3 bromo, 3 chloro.
Yeah. And what if we move to this position?
3 bromo, 4 chloro.
Or could it be this is now carbon number 1 and it becomes 4 bromo, 2 chloro? Do you know what I mean, Mohammed? So now this is carbon number 1, and if it's in this position, the chlorine, can't we just call it 3 bromo, 3 bromo. 1, 2, 3, 1, 2, 3. So it'd be 3 bromo, 2 chloro again. Do you agree?
Yeah.
Good. And if we move it here, it would be 3 bromo, 1 chloro.
But what did you do it for the first question? 1 bromo, 4 chloro.
Why did I do it like that for the first question?
Start repeating.
Why did I do 1 bromo, 4 chloro? 1, 2, 3, 4, 5. As in, what was the other alternative? As in calling it 2 chloro and... Because the other alternative would be to call it 2 chloro and then call it what? To make this carbon number 1 be 2 chloro and 3, 4, 5. 5 bromo, 2 chloro. Why would we do that? I think this is right. What I wanted to say is that these options, these last 2 options, don't apply because 3 bromo 1 chloro we've already gone through. 3 bromo 2 chloro we've already gone through. So do you see why it's important? Do you see why I'm only stating the positional groups? And I'm trying to find overlaps, and any overlaps I'm cancelling it out. Okay, so far you can see, even just with this pentane main chain with bromine and chlorine, and I haven't even, I technically don't need to go to the ends, because can everyone appreciate if the bromine was moved again and locked in this position, that's the exact same as it being locked in this position, except this would be carbon number 1 now, right? So technically I've exhausted all my isomers, all my positional isomers in the pentane main chain. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different isomers within that pentane main chain. And you can try working out and getting me all the isomers in these 2 main chains, but it's a really good way to practice what to do when there's 2 different substituent groups. Akshita, question?
Yeah. You know the second variation, right? You wrote 4 bromo, 1 chloro, right? I did that, and when I did that, doesn't that just become 1 bromo, 4 chloro?
4 bromo, 1 chloro. Well, doesn't that just become 1 bromo, 4 bromo, 1?
Oh, wait. Oh, I forgot the 5th one. Yeah. No, you're right. Yeah.
Good. Yeah. I was also slightly rushing it just so we can quickly get through the principle, right? But hopefully you all understood. The key goal here is lock one substituent, move the other one everywhere, and write down the number. Do you see how I'm focusing on the number location of each of the substituents? And then what I also didn't do, everyone, which I should have done at the end, is zoom out and then ask yourself, by any chance, are any of these the same as any of these? They shouldn't be, but it's always very good to double check. Any of these number orders similar to any of the other number orders? In this case, the answer is no. Sid, question?
What is like the max amount of carbons we'd have to do isomers for?
Usually 4. So usually they'll give you 4, and they can give you up to 2 different alkyl groups, but they'll never, or halogen groups, etc. But won't give you 5. Do you see? That was my worry. The second you go to 5 or more, the isomers, they literally exponentially increase. If you have a compound with C10, for example, even with 1 halogen or 2 halogens, the isomers are like in the tens to hundreds. Okay, the most I've seen in a HSC question is 9 different isomers. We've already gone through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, if I can count right. Right? So that's why we stopped with this question. But as long as you guys got the principle. Any questions about isomers? Chain positional is a key thing. The other kind of isomer you can have is called a functional group isomer. What that means is a compound has the exact same chemical formula. Let me show you. Something like, I'll just show you C4H. Okay, so a functional group isomer would be when you have a compound of the same chemical formula, but a different functional group. An example of that we'll learn soon is aldehydes and ketones. They're compounds where, in this case, you can have 1, 2, 3, 4. We can have a double bond in this position. When we have this double bonded carbonyl group, that's what it's called, carbonyl. We have the C double bonded to an O at the end, it falls under the functional group of aldehyde. Whereas when we have a C double bonded to an O in the middle, it falls under the functional group of a ketone. And when we say functional group, remember, we're talking about sites of reactivity. It's the difference between a single and a double bond, the difference between a double and a triple bond. Those are all 3 different functional groups. The same with this case. These are 2 different functional groups. So whenever they ask you about functional group isomers, you're trying to create a completely new functional group. You don't care about main chains. You don't care about positions. It's just solely, can you create another molecule that has a completely different functional group? If so, that is an additional functional group isomer. Any questions so far? All right, good. Let's do, already done this one. Can you guys do, we've already gone through that. Can you try this one for me? Option D. It should be a bit easier because it's only 3 carbons. Okay. Good. I'll give you all about a minute to try getting me all the different functional groups for this compound. Ethan, question?
Wait, sorry, what are we meant to do again?
Isomers, right? Topic is isomers. Yep.
All right.
Good. We've got one answer. Sid, I'll get you to start off then for us.
So there's only one chain isomer. And then the positional isomers. So I fixed the chlorine in the first position.
Good.
So 1 chloro, 1 io. Is it?
Iodo.
Iodo.
Yeah. Good.
Then 1 chloro, 2 iodo, and then 1 chloro, 3 iodo.
Good. 1 chloro, 1 iodo, 1 chloro, 2 iodo. If you move it here, it'd be 1 chloro, 3 iodo. And good. And if you bring it here and here, it's the exact same. All right. So very good. Good. What if you fix it in the second position? And I'll get Ethan to answer this one. Chlorine is now fixed in the second position. Ethan, what would you call this?
You get 2 chloro, 1 iodo, and 2 chloro, 2 iodo.
2 chloro, 1 iodo. And if you move it here, it'd be 2 chloro, 2 iodo. And what if you move it there? What would it be called, Ethan?
It'll be same as 2 chloro, 1 iodo.
Very good. Right. Good. And what if we move the chlorine in the last position? Do we even need to check that, Akshita? Why not?
You wouldn't need to check that because it would just start with 1. It would just be 1.
Very good. So we've got a total of how many isomers, Britannia?
5.
Good. How many different positional isomers do we have in each main chain? It's 3 and 2, and we have 2 different chain isomers. Very good. I think that's it on isomers, everyone. You did well. Just make sure you understand isomers because they're a really easy point to make silly mistakes. As you can see, if you miss one naming or you accidentally overlap, you'll get the answer wrong. Okay. Very good. Now, before I take you through naming all the other different functional groups, now that you understand alkanes, alkenes, alkynes, I want to first tell you what the different functional groups are, and then we'll zoom in deeper and start naming each one. Okay, we've also gone through naming haloalkanes. They're technically regarded as a different functional group as well. But as long as you can appreciate, they have the same level of priority naming as an alkyl group. Okay, the reason that they're classed as a different functional group is because the addition of a halogen will change the reactions that compound can engage in. Good. Let's talk about alcohols. Now, the functional group that makes a molecule an alcohol is the OH group. Okay. Now, you'll notice here general structure. You'll see this structure R. R just represents any hydrocarbon chain. R is just a template. It could be an empty box. That's how you can kind of think about R. Okay, so all this is telling you the general structure consists of some hydrocarbon of any length, and attached to any part of that structure will be an OH. Could be attached to the middle of the structure, could be attached to the end, but they're just showing you there is an OH attached to it. Okay, good, good. Now, one small point to note is for HSC Chem, you're not going to be learning alcohols per se, you'll be learning alkanols. And this specifically refers to alkane main chains that contain an OH group. So you won't be looking at alkenols or alkynols. It'll solely be alkanols. So the word alcohol and alkanol can be used interchangeably, but just understand alcohol is the umbrella term. And underneath, specifically when you have an alkane main chain, it is an alkanol. Good. What about aldehyde and ketones? Aldehydes and ketones both have the same functional group. The difference, everyone, is the position. Aldehydes have this double bonded to an O at the end, whereas ketones have this carbonyl group, this carbon double bonded to an O in the middle. You can see there's an R and an R dash. The R dash is to show you this is another continuing chain of carbons and hydrogens to the left and to the right. Whereas here you can appreciate for an aldehyde at the top, there is only a hydrogen at the right, meaning this is the last carbon of the molecule. Okay. Good. Now, in terms of the suffix, just like with an alcohol where we end in ol, with an aldehyde we end in al, al. The way I remember this is aldehyde has an al in its name. And I remember al means the aldehyde is all alone. That's my little mnemonic way to remember it. So now I remember the carbonyl group, which is a functional group, is all alone at the end of the structure. Okay? And the suffix will be al. Example here, you guys can see the main chain is a propane. So we're going to call it propane. And what we do is we take the E off and we add the suffix al. And this is simply propanal. Okay, I'll teach you naming later. But for now, I just want you to focus on what the functional group is and what the name of that functional group is. Okay, so ketones, aldehydes, same carbonyl functional group. The location is the difference. Good. Actually, if you remember, which one would have a higher melting boiling point?
Ketone, I think.
Very good. Good.
Yeah.
Do you know why or guess?
Ketone. Because isn't it because of the structure? Like because it's the aldehydes in the middle. I mean
Aldehydes at the end.
sorry, aldehydes at the end and ketones in the middle. Like I'm pretty sure it's because of the structure that it's harder for the bonds to break.
Good, you're right, but do you know what part about structure? We'll go through it, don't worry. But I'll explain exactly why that is the case. It makes a lot of sense when you think about the electrons and polarity. But we'll come back to that. Okay. Okay. Again, next, carboxylic acids. You guys already know the key carboxylic acid, the main character of chemistry and acids, ethanoic acid. So you should know it ends in oic acid. Okay. And the functional group is a carbon with a carbonyl group, but also with the alcohol group. So there's technically two functional groups that have come together at the same carbon. Okay, you can see here, ethanoic acid is your key example here. Now, there are a few more compounds. We'll talk about amines first. Now, amines occur when you combine ammonia to a hydrocarbon. What happens is the NH3 looks like this. When it combines with the hydrocarbon, what happens is these two hydrogens pop off, and what ends up happening is the nitrogen will connect like this to the carbon chain. So you see it's NH2 at the end because one hydrogen came off when it combined with another hydrogen from the hydrocarbon chain. The general structure of an amine is hydrocarbon chain, then the ammonia, but there's two hydrogens instead of three. The third came off, so the amine could form the bond with the main chain. Okay, good. Now, amides, they're formed when you have a carbonyl group and an amine group. We'll go through how they're formed, etc. I don't expect you to memorize all of this just when I'm talking to you. As long as you can appreciate, yes, this is an amine, and I can appreciate up here is a carbonyl, and this must make an amide. Okay. Now, to talk about esters, etc., we'll come back to esters, and the reason being, you need to first understand the other functional groups before you can understand how an ester is made. Okay. Any questions so far? Before you guys go, quick quiz. I'm going to ask you what the functional group names are. Okay. You can just say OH or NH2, etc. Britannia, what's the functional group of an alcohol?
OH.
Good. Ethan, functional group of a aldehyde and ketone. Ethan, functional group of aldehyde or ketone. Any ideas?
Oh, sorry. The functional group for ketone should be C and a double bond with O.
Good. What about aldehyde?
CHO, yeah.
No, same, exact same. Aldehyde ketone have the exact same carbonyl group, which is a C double bonded to an O. The only difference is an aldehyde. Sid, what's the difference between an aldehyde and ketone then? If they have the same functional group.
Aldehyde is the oxygen's at the end of the chain,
Good.
while ketones in like the middle.
Very good. Mohammed, on to you. What makes a compound a carboxylic acid? What does it need to have?
And
So it has a carbonyl group, but it also has a. Think about ethanoic acid. Come on.
OH.
Good. It's carbonyl group and OH. Very good. And for a compound to have a amine functional group, Akshita, what's the functional group called?
It should have the ammonia, the NH. Yeah.
Good. And for it to be an amide, what does it need to have? This is probably the hardest one to remember because I very quickly went through it. With Anya? For it to have an amide. With Anya?
Was it the
There's a carbonyl and there's an amine. So that's an amide. We'll come back to that.
NH2 and the double bond O?
Yeah, there's NH2 with a double bond O. Exactly. So that what I drew at the bottom, that's an amide. Very good. It's all right. We'll go through all of these one by one. It was quite ambitious trying naming everything, but I think isomers took a big chunk of our class because it is very high yield. Okay, good. All right, good job, guys. One thing I wanted to ask. So I only have my anatomy cadaver labs for my master's every fortnight. So what that means is next week we'll definitely only be able to start at 5. Some weeks we'll be able to start at 4. Would you want me to message on Teams on the days we can start at 4 and we start at 4 instead? Or would you prefer to just have class at 5 regularly? What would work better for you? Can you hit the raise hand icon? Would you prefer to start earlier if that's a possibility on the day and get notice on the day? Got 2, 3, 4. Okay, so majority rules. That would mean the only thing I'd need from your end is to make sure you are checking Teams the morning of. Okay, check Teams the morning of. Check Teams just to be safe at 4 o'clock as well. But I will tell you by midday whether we're starting at 4 or 5. Or alternatively, what we can just do is we can fix it. And what I mean by fix it is if you can put it in your calendar, every alternate week will start at 4. So normal time. Okay, so next week we're starting at 5. Can you all write this down? Next week we're starting at 5. The week after we'll start at 4. Okay, and sometimes in my anatomy labs they finish early at around 2. If that's the case, I can still start at 4. So best bet would be, let's just come to one final way to check so we're all communicating and on the same page. Can you all do me a favor? Check your Teams at 3 p.m. every week. But usually we're going to be alternating, meaning next week will likely be 5, the week after 4, the week after 5. But if you check Teams by 3, definitely by 3, I'll let you know whether we start at 4 or 5. Is that all right with everyone? Okay, good. All right, guys, have a good week. Thanks for staying for class. I know it's dark now. So go out, have some fun, enjoy, eat some good food, get some rest for those of you who aren't sleeping too well. You need 7 hours. There's only like 2% of the population that can survive on 4 to 4.5. They're absolute aberrants. But most of us need the 7 at least. Okay. All right, have a good week. See ya.
Thank you, sir.
Bye, Akshita.
Thank you.
All right, bye, sir.
Bye.
Thank
See
you.
you guys.
Access to the 7 notes.